Hey everyone, this is Tony Bechet, your Physics 2 CSI, and today we'll be going over some of the Bohr atom stuff and the light spectrum stuff. Okay, so what I plan to do is just to go through the questions that I have and kind of touch on the topics through that. So let's go with the first question. So how much energy in mega electron volts would you obtain if you completely convert a nucleus of 12 nucleons into free energy? So we know that a nucleon is a proton and a neutron. So this is more than just converting 12 neutrons, 12 neutrons into mega electrovolts. What we have to do is use that Einstein equation. So E equals mc squared. But what is the mass in this case? The mass is going to be 12 protons and then 12 neutrons, and then times c squared. And so you basically plug in this stuff here, and you'll get a number. That number is going to be in joules, though, and we need to convert from joules to mega electron volts. And there's stuff in the lecture that goes over that, so that's definitely something that's doable. So let's go on to the second question. This one's a little bit more complicated. In one experimental setup for studying interference patterns of electron waves, 2 slits are created in a gold-coated silicon membrane. Each slit is 62 nanometers wide and 4 meters long, and the separation between the slits is 272 nanometers. The electron beam is created in an electron gun by heating a tungsten element and by accelerating the electron across a 600-volt potential. The beam is subsequently collimated using electromagnetic lenses, and the collimated beam is sent through the slits. Find the angular position of the first order bright fringe. So we know that this is a double slit interference question. So what we're going to have to do is use a double slit interference equation, which is d sine theta equals m times the wavelength. We know D is in the question, right? D is in the question. We know we're trying to find the angular position. We know what M should be, and we just need to find the wavelength. So how do we find the wavelength for an electron? Well, in the lecture, we went over that the wavelength equals h over p, and just as a little hint, just p equals the square root of 2 times the mass of the electron times kinetic energy times k. So now we need to know how to convert this into this. And so just as a hint, 600 volts equals k equals electron volts. Okay, so that'll be a good way for you guys to convert. And then once you figure out what the wavelength is, it's just plug and chug from there. So number 3, if a 1 picometer electron beam of a transmission electron microscope passes through a 2 micrometer circular opening, what is the angle between the 2 just resolvable point surfaces for this microscope? And so the thing to keep in mind, this is for the last lecture, and so we know that the angle equals 1.22 times the wavelength over the diameter of the aperture. Here is also plug and chug. The important thing is, sorry, this is the wrong one. The important thing is to know when to use these equations for which type of problems. Let's go on to number 4. Calculate the electronic transitions in hydrogen, which will lead to emission of visible light. So this one requires a little bit of thinking, okay? So we can kind of go two routes in this way for this. Um, I skipped the question. Let me do number 4 first. So an electron in a one electron atom falls from an orbital with n equals 5 to n equals 1. What is the change in energy of the atom? And so you guys haven't gone over this yet, or you guys haven't been showed this yet, but we have to use the Rye Break equation for this one. Okay, and so the Rye Break equation is 1 over the wavelength equals Rye Break's constant times 1 over n squared final. This is the final energy level that we're getting to, minus 1 over n squared initial. Okay, and you kind of just plug in stuff from there. So Rye Break's constant is R equals 1.10 times 10 to the 7 1 over meters. So this is the way to do it. This is the way I would do it. The thing is, once you figure out what the wavelength is, we need to figure out the energy. So how do we convert between the wavelength and energy? We use E equals hc over L. So that will give you the energy because these two are constants. Okay. There could be another way of doing this where we use, since it's a hydrogen atom, we can use negative 13.6 electron volts over n squared and calculate it that way and kind of subtract the change in energy and find it like that. Either way, whichever one seems easier to you. Number 5 is along these same lines. So calculate the electronic transitions in hydrogen, which will lead to emission of visible light. So we can again use this Rye Break equation. We can use this Rye Break equation again, and but now we know that we're looking for this particular wavelength, right? So that's where we're plugging into lambda, and we can experiment with different end states, or you can use this equation and see the possible wavelengths that are emitted. Actually, yeah, the second way might be a little bit easier to do that with. But try both ways and see what you guys get. Number 6, find all the wavelengths that would appear in the spectrum of hydrogen atoms initially in the n equals 5 state. So same thing as the other two. We can use the Rye Break equations. For this one, it would seem that, yeah, the Rye Break equation would be the easiest one to use because it directly outputs the wavelength. So yeah, I would say use this equation. And then the n equals 5 state will be your initial. We know the Rye Break constant, and then and then we can just change this final state and get all the wavelengths. So you should get 5 different wavelengths. They're they're gonna be 5 to 4, 5 to 4, 5 to 3, 5 to 2. So only 4 wavelengths. Yeah, I'm sorry. I knew that sounded wrong. 4 wavelengths. This one gets a little bit more interesting. I usually don't do multiple choice, but I did it for this one. So a pair of protons in an atomic nucleus repels each other. Okay. But they are also attracted to each other. Why? So without looking at the answers, we know already that the atom experiences 2 types of force, right? It experiences a nuclear force, and it also experiences a Coulomb force. So I want you to ask, which one is long distance? Which one is short distance? Which one is strong? and which one is weak. These are all in the lecture slides, so look through, and the answer should be clear from here. Okay. So in a sample of hydrogen atoms, electrons make transitions from n equals 5 to n equals 1. If all the spectral lines are observed, then the lines having the third highest energy will correspond to. So what you have to do is compare the energy levels of these electrons, of these electron transitions. So what do you guys think would be the best way? You can either use the Rye Break equation, or you can use, I believe you can use this hydrogen equation for energy, and compare the different energy levels that are shown. So what you need to do is be E final minus E initial to see the change in energy compared to the two transition lines. And so yeah, that's the worksheet. That's all I have for today. Please feel free to email me if you have any questions. My office hours are Tuesday and Thursday from 2 to 3 p.m. And your final is coming up, so please, if you need help, please don't hesitate in asking for it. And yeah, thank you guys for watching. I hope this helped.